So would you consider your rock a composite? That is formed of several phases? Would you consider your rock an homogeneous material or an heterogeneous material?
Heterogeneous.
Right, so it's kind of a composite. So in this case, the material may be homogeneous, plastic, glass, silicon carbide, or heterogeneous, like fiber or particle reinforced composite. You know, concrete is a composite material. What makes a material emissive is that they can contain brittle components. These are good for acoustic emission energy production. The heterogeneity for arresting cracks, allowing accumulation of substantial damage before failure, and also stress field concentrated rather than global. This permits crack to arrest lack of available energy to drive it further. So acoustic emission has been applied in fiber-reinforced composite material on plastic matrix with thermoplastic or thermosets, metal matrix, ceramic matrix, other materials like cement or rubber. And this industry is huge and growing importance starting in aerospace and then everywhere else. Nowadays, we have an application for these composite pressure vessels. Some of them are a combination of a metallic liner with a reinforcement layer of a composite material, either fiberglass or carbon particle composites, carbon fibers. So we know that the composite is formed in this case by a fiber and a matrix. It has an increased use because of the good mechanical properties. Some of the reinforcements used are glass, carbon, ceramic fibers, resin, and other matrices. There is a variety of manufacturing techniques material formed, and they have excellent acoustic emission properties. These are some examples of the formation mechanisms that can be encountered on fiber-reinforced composite materials. You can have defects happening on the matrix only, like transverse cracking, splitting, in this case, the laminations, like in this case, fiber breakage, single fiber break, like in this case, or multiple bundle fiber breakage, or a combination of pull out and matrix damage. So acoustic emission from composite materials, we know that acoustic emission is excellent for composites because of this behavior. There is a large amount of acoustic emission, and they can go from big range from good to bad. They can be very strong increase before failure, which gives us an effective warning. There is continuing acoustic emission in load holes that is revealed at high stresses. Previous damage gives frictional acoustic emission, indicated by the Felicity effect, and you will observe acoustic emission happening sometimes during the unloading of the test piece. This is very rich, informative, amplitude distributions, and these effects are also present in metals, but are much stronger, easier to see, and immediate useful in composites. This is some example of plots in composite materials. The first plot here on your left top side, we are plotting basically the accumulation of heat versus time. So the y-axis indicates the accumulation of heat versus time. All right? The plot below is the plotting of the load applied, this case is in pounds, versus time. So you see in here we started at 2,500 pounds, and then there was unloading with my mouse, unloading up to about 1,500 pounds. Then there was an increase of the load up to about 4,000 pounds, and you see the small increase of acoustic emission at this point. When we unload here, there is no accumulation of heat until we start to increase the load, and you see the corresponding increase at 200 seconds, about 200 seconds, when we go above the previous maximum load here. Okay?
Okay.
And it continues increasing the number of hits as we increase the load here. Then, as you can see here, we go above 5,000 pounds. And what happened here, maybe we created some damage in this composite material that even we are unloading now, there is also an increase on the accumulation of acoustic emission signals. So you see the relevance here that when there is present damage, we have the presence of acoustic, secondary acoustic emission maybe related to frictional due to the formation of new surfaces on cracks created in the material. Now this is another type of plot in which you see the amplitude of the signal versus time. And the coloration is related to the number of hits detected at different times during the loading schedule. So you see at about 100 seconds is when we are increasing the load, and this is the corresponding generation of hits and the amplitude generated. But you see, most of the hits were low amplitude. When we are increasing the level of load, now the number of hits of higher amplitudes start to increase, and also the amplitudes of the signals start to increase. And by the use of this very simple amplitude distribution plot, you can determine if you are generating damage in your test piece. In this plot here on the lower bottom right, what we are plotting basically is the number of hits versus the amplitude. That's why it's called an amplitude distribution. So you count the number of signals at different amplitude levels. And you can see as the damage started to increase, you will observe an increase on the number of signals detected with high amplitude. Okay?
Okay.
Now what happened when we produce or stimulate those acoustic emission sources in the materials. As we increase the amount of matter that is involved during the movement of those sources, is going to increase the amplitude of the signals detected. What is the meaning of this? When we are talking about atomic movements, you see the corresponding decibels of amplitude to that atomic movement or molecular movement. It's very small. Remember, the reference scale for the classification of the amplitude of signals is referred to a 1 microvolt signal, meaning that a signal of 0 decibel of amplitude is referred to a signal of 1 microvolt size. So when we start to increase the amount of matter in the material, if we have dislocation movement or precipitate or the microcasting of the magnetics, you see the microvoltage equivalent of those movements increases, and so then the amount of decibels. Then when we start to deal with movement of crystal grains, the formation of corrosion peaks, or the large fracture of crack jumps, so the amplitude, the signals is much larger. When we have breaking off of precipitate or non-metallic inclusion, you see also the equivalency of those amplitude signals. Any comments, any questions here?
No.
No? Are we good?
Yep.
All right. We already saw this diagram where we can somehow we characterize properly our signals. We can relate them to different phenomena in our process. We saw the Kaiser effect, the Felicity effect, the Felicity ratio, the acoustic emission behavior on heat loadings. And this is an example of how to track damage with acoustic emission. So this is an example of a blade of a windmill. What we are plotting here, you see the red line is the percentage of load applied, and the green line is the absolute energy released by the acoustic emission signals detected during the load schedule. So let's start here at the beginning. The first load increase, you see there is a corresponding release of energy from the signal detected. And they go even after we hold the load at this level. All right? Then we unload that blade here, and there is no change, or there is no energy released by the acoustic emission signal detected, or there is no actually acoustic emission signal detected at this point. Then when we start to increase the load again, you see the release of energy acoustic emission signals when we reach the previous maximum load at this point. it continues releasing energy even during the whole period. Okay? But then again, when we reach this point and start to upload the blade, there is no energy release at this point. Again, we continue the loading schedule, and we continue now increasing the load. You see, from this point to this point, there is no energy release until we reach the previous maximum gain. So there is energy release here, even during the whole period. Now it is interesting what starts happening here. When we unload, even there is a small increase in energy release during the unloading of the blade. What do you think is the meaning of that energy release during the unloading, not during the uploading? This could be made related to the evolution of damage at that point, at this level of load. And if you see the corresponding energy curve at the bottom, we are plotting here the energy released by the signals detected. You see that all of these signals detected here, most of them, the release of energy is very small. And they start gradually increase at this point, and then further at this point. But the release of energy here is very small. Okay? Now, if we continue the load schedule here, we start to increase here, fall here, and there is a small energy release here, but with just very few contribution in the whole energy. And then we continue increasing, and we see this jump again of energy release. And we start to see more release of energy at this point when we continue increasing the load. But what happened at this point? You see there is a change in the slope of the curve of energy, and that is known as the knee in the curve. And this is indicative of imminent failure of test piece. All right? Any comments, any questions? Is it understandable?
So when there is an absolute energy, when the load is decreasing, they are frictional behavior, right?
Yeah, they could be related to frictional phenomena that are due to the presence of maybe new cracks or the increase on surface area related to the formation or growth of cracks in the material.
Do they have possibility for both behavior? One is friction and the other one is, as you said, the growth of friction surface like that.
Yes.
Even the load is decreasing.
The frictional, they are more notorious during the unloading.
Yeah.
And the crack formation, they are more notorious during the uploading and during the whole periods.
No, I mean the period when the load is decreasing.
Those could be related to, basically to the frictional noises.
Okay.
All right. So this is the whole test. Now what we are plotting here is the accumulation of the acoustic emission energy versus the load applied, just to observe the Kaiser effect and the Felicity effect. So if you relate the laters to the load schedule that we apply here, you see this is the first load applied. This is this one. This is the first hold at this level of load. And then we decrease the load here and increase it again. And we didn't see any increase in the cumulative acoustic emission energy until after the previous maximum load. So in this, the Felicity ratio is 1. In this one, the Felicity ratio is 1.06. But in this, we started to see a decrease in the Felicity ratio, which is indicative of the damage evolution in this case in this turbine blade. All right, now if we magnify this area here, you can see more clearly the effect of the Felicity ratios here. This is another example of a composite ring with damage. This is the Felicity plot, and you see there is nowhere where the accumulation stops or decreases. It is increasing all over the plot. So again, this is the load, and this is the energy release. And this is the load schedule. So you see it's completely flooded of acoustic emission signals. It doesn't matter if we are increasing the load, holding the load, or loading. It means that in this case, this composite is completely damaged. So you can see clearly the difference between a sound material that is developing damage with a damaged material. All right?
Okay.
But I mean, a damaged material that you see the material and apparently with your eye is in good shape. But in reality, when you tested it, it's not in good conditions. Okay? This is a schematic of the turbine blade that was tested in this example. And I already explained this, the Felicity plot, in which we plot in the x-axis the percentage of load versus the accumulation of acoustic emission counts. But also we plot the location plot. The green squares or the green numbers represent the acoustic emission sensors mounted on this turbine blade. Now this is an example of formation of clusters of signals. Cluster means accumulation of signals on a specific area where we are locating signal. And these are signals detected by several sensors, meaning these are events. Okay? And the coloration, you see the green, the yellow, the red, they are related to the amount of energy that they release, meaning that the red coloration is related to a higher level of energy. So from these location plots, you can tell where the most critical damage is happening because of the energy release in these locations. All right?
Mm-hmm.
Is it understandable? Is it explanatory?
Yes.
All right. This is another representation after analyzing with multi-feature analysis for crack detection. In this example, we plot the Y position versus the X position versus the absolute energy of the signals or the event. In this second plot, we are plotting again the Y position versus the X position, but now instead of using the absolute energy, we are plotting the frequency centroid of the signals. This is another acoustic feature extracted from the acoustic emission signals. And we are graphically filtered just to show, in this example, the signals with a frequency centroid less or equal than 75 kilohertz. So in this example corresponds to the signals detected in this particular area. And they are related to this type of damage. Comments, questions up to here?
No.
No? Okay. This is an example of a composite fuselage testing. In this particular example, it was used different inspection and monitoring methods. It was used strain gauges, strain photogrammetry, acoustic emission, frequency response, flash thermography, and computer-aided tap test. So these are the results of these different techniques. You see the result of the microstrain versus time. This is the strain photogrammetry. This is acoustic emission. This is the amplitude versus frequency in kilohertz. This is the frequency response and the computer-aided tap test. So in this particular example, what I want to show you here is that the most deleterious damage happening at this particular frequency ranges. Okay. This is another example showing different damage configuration on test panels. We have a baseline of on damage test panel. Then we have a repair patch loads of a 10 inches diameter circular hole outer face sheet. Then we have a blade separation with a circumferential notch. And then we have a longitudinal notch and blade separation. And finally, we have an inclined notch on blade separation. So these are the most critical damage. And this shows strain gauges and the sensor used for this particular test. So focusing on this plate, the CP5, with a longitudinal notch repair of 10 inches and half an inch depth. And after applying the loading schedule, you can see the number of signals detected after this loading schedule and where they were located in this location plot. After the second schedule, you can see how the areas between the 80 sensors start to populate. And if we continue applying the cyclic load, you start to see accumulation or formation of clusters in specific areas. And this is the final accumulation, and you can see the number of detected events. You see that there is some accumulation at the tips, in this case of the notch, that's related to the opening of the crack. And in some far field region. Okay? So we saw all this activity when we consider the conditions for locating events, at least the signal being detected by 3 sensors. So with these 3 sensors, you see all of this activity happening around here and around the node. But when we increase that a signal being detected by at least 5 sensors, now what it happens, it restricts the location to just where the notch is, where the tips of the notch is. And it removes the far field events located previously. So these are some filtration techniques or filtering techniques that are used as strategies to tweak, in this case, the location of damaging events. Comments, questions up here?
No.
Okay. This is the image of the CAD image, which is representative of the damage detected around the notch. And this is the 3D representation. This is the notch. You see the cluster detected around the notch. This is the increasing events, the execution, Y position, and these are the far field events detected with these sensors. The cluster located around both this bone edge and notch tip, and this bone is much noisier than the notch tips. When we apply the filtering, now we see the real accumulation at the notch tips. The energy released from both notch tips is much greater than any other events clusters. You see, this is the same plot, 3D plot, but in this one we are plotting the number of events detected, and in this one we are plotting the energy released by the signals. Even though we have a lot of events in this area, the amount of energy is not as relevant as the amount of energy released in these areas around the notch. So you see the difference of using one or another acoustic emission filter. Okay. This is now the example for the CP6A event location. If we go back to the this one, this is a panel with the inclined notch of dimensions 10 inches by 1/2 an inch, oriented 45 degrees in the plane. Again, you see the different loading schedule, the number of events detected increasing from 26 to 94. They start to accumulate in the location. They continue accumulating. Now they are 44 events. Now they are 447 events until you reach 2,355 events. Again, you see the clusters. We filter by the number of sensors detecting the events. Now we narrow search around the tip of the notches. And the direction of visual damage propagation correlates with the located acoustic emission events. Comments, questions up to here?
Yes, I have. I have a question.
Okay.
I want to know how you remove the far-field event.
If you go, let me start to use A-Wing to start to get you familiar with that. Okay. Okay. When you go to A-Wing, can you see my screen?
Yes.
All right. So you are familiar with this screen. Have you seen this screen on your software? We are going to go in further depth later, but just to answer your question, when you go to the acquisition setup and you go to the location, if you use a location group,
Yes.
let's say 2D planar location, and you specify the wave propagation velocity, you specify the event definition value, and you specify the event lookout value, then at the end, you see the number of sensors detecting one signal. You can modify this number of sensors.
Yes.
The default for planar location is that the system is going to consider one event and when 3 sensors detect the same signal. So what we are doing in the example that I was showing, we are increasing the number of sensors instead of 3 to 5.
Yes.
So weak signals are not going to reach the other 2 sensors. And that's why we are filtering out those weak signals. And that's how we are concentrating the signals. Where is the example? Here. We are concentrating the signals on these areas only. because now instead of using these sensors to detect the event, we are using 5 sensors to detect the event.
Oh, I see.
Okay?
Okay, thank you.
All right. Let me go to the next. Are we okay if we continue with the same next slide?
Yes, but how many slides are we gonna cover today?
It's 15 minutes to 9 on my clock. I think we can cover 2 more slides today, and we can finish them tomorrow.
And what about the rest of the days?
The rest of the days is going to be basically hands-on. I am going to show you all the parts of the software. We are going to interrelate all the things that I am showing you today on the basics, where you can modify, you can adjust in your settings, and we are trying to do some practical demonstrations.
Okay, I see.
All right? But it is important for me to explain to you all this basic information.
Yeah, I agree.
Okay? All right, so the next one is a very practical presentation. It is related to the sensor coupling and mounting. This is the synopsis for this lesson. In acoustic emission, we need the coupler to have an effective connection between the sensor and the test piece. Why is that? If we apply a coupler in the sensor and the test piece, what we are going to do is that the sensor tracks the motion of the surface of the test piece. Remember that what we are detecting with the sensor is movement, okay? And that movement is transformed or transduced into an electrical signal. We have different choices for couplers. That's a matter of practicality. We have adhesives, or we have greases, or other materials together with mounting devices. The surfaces must be appropriately prepared. They have to be preferable, free of roughness, free of any curvature, because they are going to have an effect on the attenuation and the detection of the signal. Now we need to check how effective is that coupling between the sensor and the test piece. And one technique is the so-called pencil break. Okay? This technique matters in order to be consistent at the moment of breaking the pencil lead. We have to have a difference between readings between 2 and 6 decibels of difference. And that will depend on the test procedure. Usually, the least different we have between the readings, the best coupling effectiveness we are going to have. I hope you have one of these.
Yeah, we have it.
Yeah, 0.2 millimeter 2H hardness.
Yeah.
Yeah.
Actually, 0.5.
This is 0.3.
Oh, okay.
All right. So that's what we use to check the coupling of the sensors. So the goal is that a channel sensitivity that is high, stable, consistent, and reproducible. It is the responsibility of the technician, and this is one of the most significant areas in which this part needs to be supervised, and you need to practice to get the right results in the variety of situations that will be encountered. Why coupling is needed? What do you think we need coupling for the sensor and the test piece?
Because as you said, do not allow the surface move.
Exactly. It comes down to the theory of surfaces. Dry contact doesn't work because the real contact area is minimal. And it's like when you are in a car riding on its suspension. The body isolated from the bumps in the road. Okay? So the mounting requirement, the sensor must be held in place for the duration of the test. There is a strategic choice of adhesives. It can be an adhesive, it can be a grease or raw material with mounting devices. The necessary couplant characteristics is that they have to be chemically compatible, they wet properly the surface of the test piece, and they don't affect, they don't corrode, or they don't attack the surface of the test piece. They stay in place, meaning that they don't drip or they don't evaporate. They are compatible with cleanup requirements, and they effectively transmit the acoustic energy. So basically, the use of the couplant is to eliminate the air interface between the wear plate of the sensor and the surface of the test piece. From practical experience, we have to bear in mind the curvature effect. In some pieces with a specific curvature, the use of epoxy was found to be 6 decibels more sensitive than the use of silicone grease on a pipeline of 4 inches diameter. However, in other situations, the use of SLC 70, which is another high viscosity liquid with high molecular weight coal, was reported decibel more sensitive than vacuum grease on railroad tanker, but when they were to compare in the calibration lab, they behaved practically the same. So it depends on the situation that you are working on, the choice of couplant that you are going to use. I don't know what you use for coupling your sensors.
There is a grease you provided.
The high vacuum silicone grease?
Yeah, vacuum grease.
Okay.
But actually, it doesn't have any cohesive.
Any what?
The vacuum grease.
Uh-huh.
It doesn't have any. Okay, say adhesive.
No, it's just grease.
Yeah, it's just a grease. So
Yeah,
we need additional clamps or something.
right. For the size of your specimens, I think you could use electrical tape or duct tape just to keep the sensor in place.
Maybe I hope you can show me some types of clamps. Hold on.
Yeah, I have some examples here.
Yeah. Okay, thank you.
Okay. So we know that for experience that the surfaces are not perfectly flat, and with dry contact, the true contact area may be only a small fraction of the apparent contact area. The roughness of the surface is important. In your case, I don't know how smooth or how rough your rock surface is, but in the absence of coupling, the coupling of the acoustic wave depends on the true contact area. It is weak and very dependent on the contact force. And for this, we have a choice of coupling that will have a greater effect as the amount of coupling becomes greater. What is the meaning of this? It has a greater effect on rough or curved surfaces, and it has less effect on flat or smooth surfaces. Now, this is more in-depth information. The mechanical movement or the acoustic emission, how they travel inside the material, we have out-of-plane movement or component by the underlying motion, and the governing factor in the material is the compressibility of the coupler, which will not vary normally from one material to another. So for this motion component, the choice of coupling is not very important. But when you are trying to detect the in-plane motion or the in-plane component, the important factors are the shear modulus and the viscosity of the coupler, which may vary enormously from one material to another. So what I'm trying to say with this is that depending on the type of motion that you are trying to detect, sometimes you have to use very specific couplings for this. And unless you include air, which is so compressible that it hardly couples solid to solid acoustic waves at all. In practicality, some greases and gels such as UT couplings are designed to slide easily, so you could expect them not be a good acoustic emission coupler for in-plane motion. So we have to have some space preparation. What are the considerations? This is just for, don't take into account this. But we need to have a surface condition free of dirt, as smooth as possible, with very low roughness. And in your case, I don't think you use any paint, right? And we need to establish a test procedure that specifies how to mount or to couple properly the sensor, and what is the activities that we are going to do to make sure that the sensitivity of the sensors are okay. These are some commonly used couplings. We have the most common is the greases, high vacuum silicone grease, adhesives like epoxies or hot glue, glycols that can be water soluble, of some very specific chemical compound. Then we have high and low temperatures, like in the automotive industry compounds, specialty epoxies, exotic materials, waveguides that are often preferred when you have high temperature application. In the following slide, we also illustrate the use of the electrician tape, block tape, magnetic hold downs, glycols, adhesives, dry coupling, and epoxy on a very small test subject. This is, for example, the use of the electrician tape. This is the sensor. You apply a layer of silicone grease on the surface of the sensor and the test piece, and then the electrician's tape, you use it to maintain the sensor on place. These electrician tapes have a good stretch. It adheres only to itself, so it works only if you can wrap it around the test article. This is inexpensive and easy to find. I don't know in your specimen, where do you mount your sensors?
What?
In your specimen. What is the shape of your specimen?
Shape?
Yes, the shape.
Cylindrical rock specimen.
Let me open this.
50 millimeters of diameter and 100 millimeters for height. We have two types. The other one is cubical.
Okay, so you have a cylinder.
Yeah.
And where are your sensors mounted?
On the surface of the
cylinder?
Yeah.
Okay, in this area.
Yeah, like that.
How many sensors do you mount?
Usually 6 to 8.
6 to 8, okay. And some of them may be here, some of them may be here, okay. And you use only the high vacuum silicone grease?
Actually, first of all, when we use vacuum grease, we cannot attach sensor directly on the surface of the granite specimen.
Okay.
Granite absorb the vacuum grease. Anyway, so there is a plastic membrane on the surface of the granite, and we attach sensor on that surface with wax. Not vacuum grease. We haven't used any vacuum grease.
Okay. And how is the sensitivity of your sensors?
We use nano 30.
Yeah.
What do you mean? How does it?
Yeah. How do you check the sensitivity of the sensors? With the pencil brake, or how do you check it?
Actually, that's actually one of the important parts we want to learn.
Okay.
Through this session, because actually we don't know the exact way to carry out pencil lead brake test.
Okay.
And also the reason for that. So that's why that's what we want to have explanation from you.
All right. So this is the first of the coupling techniques using electrician's tape. This is another example on composite materials using duct tape. This green stripe. This is not supposed to stretch. It adheres fairly well, but is temperature dependent and primers available. It is not expensive, it's easily obtained, and you will find that some brands are better than others. This is the most widely used for non-metals when you have access to only one surface. So you can see the way to use it here. This is for holding down the sensor with previously applied silicone grease between the sensor and the structure. But also when you have external preamplifiers used with the sensors, these are used to hold the preamplifier. This is another example of coupling. It is used silicone grease in between the sensor and the test piece. But now, because of this structure is magnetic, we use magnetic hold downs to keep the sensor in place. These are good on steel structure only, and there are various designs available, including your own. However, they are rather expensive, and it takes skill and understanding to get consistently good results. It's a very popular solution for repetitive testing.
I have a question.
Yes.
Does that magnetic doesn't affect to the signal from the target?
No.
Not at all.
No. The sensor is isolated. It's grounded.
What do you mean exactly?
It's grounded internally. The crystal element
could you
or
show,
the piezoelectric.
Could you briefly draw the cross-sectional?
I have a presentation with the sensor. We can go there if you want.
Okay.
Let me there. Where is the sensor? No, it's not here. Nope. Let me find it quickly for you. So you see this this presentation that we have for the sensor construction. I'm going to skip all of this. This is just theory. But this is basically the concept of the sensor.
Okay.
It is a crystal, and it is connected, it is polarized. So it is connected you know, the piezoelectric crystal vibrates longitudinally and radially when they vibrate.
What do you mean?
When they detect a mechanical signal, they start to vibrate.
Okay.
Okay? And they vibrate in the longitudinal direction and also in the radial direction.
Okay.
But the shape of the crystal is such that they have matched these two vibrations. So they are in synchrony, they are coupled. And this is the schematic of the sensor.
Mm-hmm.
You have the crystal or the piezoelectric.
Mm-hmm.
Then what you see is the wear plate.
Okay.
This is a ceramic material.
Mm-hmm.
but in between the crystal and the ceramic material, the crystal is grounded and it's isolated from the external contact.
Okay.
So the magnetic field doesn't affect the performance of the piezoelectric. So every time when you have this wear plate mounted on the test piece with silicon, the movement is transmitted through the crystal, but it's only the movement, nothing else. And you have this metallic case around the sensor. That is the ground of your sensor. So the crystal itself is not affected by magnetic fields or electric currents. Okay?
Okay,
It's completely isolated.
So for
electrically isolated.
So for electrically isolated.
Yeah, electrically isolated.
So let's say when we put the magnetic near this, so all types of sensors are like this, right?
Yes.
So when we put magnetic right next to the sensor,
it is not affected.
Magnetic field doesn't affect to the signal at all.
No.
Ah, okay. Okay, I see.
And then we have different response mode. We have the so-called resonant type sensors, which mean they have a narrow frequency band of operation, like the one you have. You said is the micro 80?
Nano 30.
Nano 30, okay. The resonant frequency of that sensor is around 300 kilohertz. And that extends, if I'm not mistaken, from around 120 kilohertz up to about 500 or 600 kilohertz. That is the frequency operation range. And then we have the broadband type sensors. This covers a wider frequency range, but the sensitivity decreases. And then we have sensors with integrated preamplifiers. The ones that you have, they don't have internal preamps. We have some sensors that they have a small board with the preamplifier inside the casing of the sensor. And there are some other, like the one I showed in the picture, that they use a separate preamplifier. And we have single-ended or differential-ended electrical connection, like in this one. We have a sensor that the crystal of the piezoelectric is split, and we have a differential connector here. All right? And this is what it happens. This is what it happens initially, where the source is located inside the material. It is like a pulse, jump. Yeah. It is very short, but this pulse is very broadband. What happened around the source on the surface of the structure? If If the surface is close to the source, you are going to see a very high vibration or very high motions beside the source. As the motion is moving away from the source, the movement is going to decrease. All right?
Okay.
Then what is going to happen at the sensor? If the sensor is close to the source, the sensor is going to respond to this high movement with a high electrical signal. If the sensor is far away from the source, you see the response of the sensor is going to decrease compared to the movement far away from the source in the structure. All right?
Okay.
But in your case, you have a very small test piece. You said that is 10 centimeters length.
Oh yeah.
So I'm talking about here very long or very huge structure.
Okay, I see.
All right. That is basically how the sensors are manufactured. Those are the basic components of the sensors.
Okay, I see. Thank you.
Coming back to the mounting devices and coupling, this is another example of, you have the sensor here with the coupling and the magnetic hold down. But now in this case, the sensor has the connector on the top of the sensor. This is another example, but in this case, we are using a box. We are using an adhesive. You can see here the sensor, but now this is coupled with a thin layer of epoxy. The epoxy is the best established way to get excellent acoustic coupling, even when the surfaces are cold raw. However, because it's a semi-permanent mounting, this is the way that has caused the great number of sensors fatalities when you try to remove them. Because it's very adhered to the surface, sometimes you, at the moment of trying to remove the sensor from here, you destroy the sensor. However, there are many different epoxies on the market that can be suitable for specific application. This is another application using adhesives. This is using a rubber cement adhesive or the RTV. These are easier and cleaner to handle than epoxy. They have excellent coupling properties, especially in thin layers. The drying time is a consideration. There are techniques for dealing with this. And when the layer is thin, removing the sensor after use can be exceedingly hard. This is another example of adhesive. Have you used the crazy glue?
No, well, I don't know about.
Or the, what is the name?
Kind of gum?
I don't know if you have the Gorilla Glue.
Maybe we can search later.
Loctite. I think you should have over there the Loctite. Yeah. So that is a cyanoacrylate adhesive. These adhesives set quick in about 5 minutes or less. They don't need to be mixed. It's a single component adhesive, and it's somewhat touchy to use. They are available as either liquid or gel. The gel is preferred for handling and setting, especially in thick layers. The acoustical properties in thick layers not so trusted epoxy, but the important thing is they are not too bad to remove the sensors. So this could be one option for you to keep your sensors in place. I don't know if you have tried that.
But what I heard from Jason,
Mm-hmm.
you know Jason Dong.
Yes, I know him.
He recommended me that the best way to mount the sensor is to use mechanical force, which means mechanically, let's say, push the sensors, not just not just add something on the surface between the sensor and the test specimen.
Yeah, but your specimen is too small.
Yeah, of course.
And this is an example of dry coupling.
Yeah, right.
But you see, this is a very big pipe.
But anyway,
You see? And they are using metallic straps here.
where is the sensor in this picture?
This is the sensor.
This is a sensor?
Yes.
I mean the square shape?
No.
Only the square.
This part, no, this is just to hold the sensor.
Huh?
This plate here,
Uh-huh.
this plate here has a hole where you insert the sensor, and then you use this plate to put the straps
Oh.
to apply the pressure to keep the sensor pressure to the test piece. So this doesn't have a coupling. However, the acoustic transmission depends strongly on the contact force.
Yes.
All right? And this was a technique used in the 70s to mount the sensors in a nuclear reactor. At the time when no acceptable coupling could be found because of the operation conditions there, obviously. This is another example of dry coupling. You see, maybe you could use something like this. These are the sensors. They are held with a small plate here, and these are the straps. And then you tight with this knob the sensors. This shows the installation of a 4-inch bypass line on a boiling water pipe. In this particular case, the sensors were pulsed while the contact pressure was raised until the signal reached a maximum. So that's the way how you test this type of coupling.
Okay.
This is another coupling. This is a very small sensor. This is a pico sensor. So it's one here, one here. And in this case, we are using acoustic transmission, not emission. So in this particular case, they were testing a fiber optic material. This is the sensor. This is just a bit of epoxy to add the fiber optic material line, this line here. And this is another technique to mount the sensor by using a waveguide. These are basically used for high temperature applications. Basically, it's just a metallic rod of a specific length. This is like 30 centimeters. And it has on one end of the rod a cone-shaped base where you mount the sensor at the top, and you weld the other tip of the waveguide to the test piece, and the signal is transmitted through this rod and reaches the sensor tip. Basically, the idea of using this rod is just to dissipate the heat, and that doesn't affect the performance of the acoustic emission sensor.
What's the purpose of this test?
Sorry?
What's the purpose of this test?
We have used this on high temperature piping.
High temperature
Pipes,
pipes?
yeah. On gas turbines, where the temperature is high and the sensor cannot withstand that temperature. So we have to use these devices. So we know that this rod will dissipate the heat, and the temperature here will be lower compared to the temperature at this surface. So in this case, the test piece is at 600 degrees Celsius. And you see, just by adding 30 centimeters of length of this rod, it dissipates the heat up to 30 degrees C. That's the main purpose. Okay? And again, you couple the sensor here with silicone grease to detect the signals coming from the test piece, traveling through this metallic rod, and arriving to this base of the waveguide. But you don't use that.
Yeah.
Then the pencil brake.
Yes.
This is what you want. You have to know.
Yeah, pencil brake test.
Okay. This is the pencil brake technique. You can use a 0.3 millimeter or 0.5 millimeter diameter lead, and the length of the tip has to be around 2.5 millimeters extension. And the inclination of the pencil with the surface, it has to be around 30 degrees, as you can see here, this picture. So this angle here is about 30 degrees. And then to break the pencil tip, we apply a perpendicular force to the surface, and we need to perform this pencil brake at a specific distance from the sensor, and it has to be always the same. Usually this distance is between 5 and 10 centimeters away from the sensor. Okay?
Could you explain why? Anyway, this is the last slide, right?
No, there are some more.
I mean.
Oh yeah, this is the last slide. Yeah.
So why we are doing pencil brake tests?
Because we know the characteristics of the pencil lead we know that it has a specific hardness, and we are simulating a micro crack. Okay?
Yes.
So when you apply the pressure perpendicular to the surface of the test piece, you are generating a local stress here.
Yes.
And when you break the tip of the pencil, you are releasing energy.
Yes.
And that energy is going to propagate to the sensor, but throughout the surface, and eventually it's going to reach the sensor. So you know that breaking the pencil every time is a known source.
Yes.
It's a uniform source and is repetitive. So that's why we need to repeat this pencil lead break at least 3 times per sensor. And we need to calculate the average amplitude of the 3 pencil lead breaks. And that will give you an idea of the sensitivity of the sensor based on how good coupling you have.
So after breaking pencil lead, the sensor will detect the signal. And
Exactly.
And it shows amplitude of the signal, right?
Exactly.
So do you have to calculate or convert?
No.
No.
The equipment gives you the amplitude of the sensor in decibels automatically.
Okay, let's say we are for our test. We already put 6 sensors on the specimen, and then next step will be pencil lead break test, right? Before our main test.
Yes.
So first of all, do we have to carry out pencil lead break test for every single test?
Yes.
Okay.
At the beginning, before you start the acquisition, and at the end.
At the end?
Yeah, to compare the amplitudes of the sensors. That will tell you if the sensor moved or was affected by the acoustic emission test.
Okay, anyway, so at the beginning,
Yes.
let's say we break the pencil lead, and then the sensor detects the amplitude of the signal.
Yes.
And then, what's next?
Usually, at the distance that I am telling you, between 5 or 10 centimeters, let's say you made the pencil lead break at 5 centimeters away from the sensor. The sensitivity should be around 90 to 92 decibels.
92
decibels. 92, yeah. 9092.
Yeah, I understand. So,
and that is using 0.3. If you use 0.5, that should be higher because it's stronger, the break.
is there any range of amplitude? Depends on the. Is there any reference for the range of amplitudes? Depends on the distance between pencil lead and the sensors.
Yes, but that is used to calculate the attenuation of the signal.
I still don't understand. Anyway, I'm sorry, but I should understand this.
No, no, it's fine. It's okay. It's okay.
So, when we break the pencil lid,
Mm-hmm.
let's say we get, I'm not sure this will happen or not, but let's say we get the amplitude of 80 decibel.
Okay.
Is it possible?
Yes, it is possible.
So 80 decibel, because it depends on the many parameters of the system, right?
It depends on your coupling.
Yeah, and gain value or many.
No, the gain, you don't use the gain.
What do you mean?
The only parameter that you use in acoustic emission is the threshold.
Threshold. Okay, that gain part is also another problem for me though.
Okay, I know what you mean. Are you using external preamplifiers?
Huh? Oh yeah, we have oh yeah, preamplifier outside.
You have the 246?
Yeah, right.
Okay. So that gain is referred to the amplification of the signal. Meaning that, let's say, if you are getting a signal of, let's say, 10 microvolts.
10 microvolts, yeah.
Okay.
This is fixed. It doesn't change, right? It's kind of real value.
Yes, well, let me tell you this. You have to match the gain that you are using in your external preamplifier with the preamplification that you specify in the settings on the software. Let me go to the software. And let me show you the preamplifier. Okay, let's see. You have the preamplifier. You have this,
yes,
right?
Exactly.
You have the 246, and it has three selections.
Yes.
It uses 20 decibels, 40 decibels, or 60 decibels of amplification. And they are specified as gain.
Yeah.
Okay? This is to increase the voltage of the original signal.
Okay.
Alright?
Yeah.
So whatever you choose here, 20, 40, or 60, it has to match in the settings that you use here in the preamp.
Yes.
You have to use the 246, and you have to select 20, 40, or 60, depending what gain you are using.
Right.
The default is 40.
Yes.
Alright?
Yes.
So those numbers has to be the same. In that way, the acoustic emission system subtracts the preamplification that was added at the beginning and leaves you with the original value of the signal, the original amplification.
So when the gain value of preamplifier and the parameters here in this AV Win software are same, and then original signal I mean volts, will not change.
No,
No?
no, they not change. You have the value of the amplitude of the original signal.
Okay, okay. So I mean, is it right? What I understand?
Yeah?
It's still a little bit complicated. Anyway, so okay.
Let me see if I have an example here to show you. Let's see. Yeah, because this is important for you to understand. Training labs. Okay. You know what? Let me look for some examples, and I can show you those readings from the pencil break, and I can explain you in more detail.
You mean later?
Maybe tomorrow.
Okay, okay, I see.
Yeah. I need to look for that information. I have it, but not in this this.
Okay, okay, no problem.
All right. Yeah, but just to show you, this is part of a test. When we select, let's say, one of these signals, you see the waveform of the signal, and at the bottom you see all the characteristics of the signal. You see what channel detected the signal, the rise time, the number of counts, the energy, the duration, the amplitude of the signal in decibels, the average frequency, the root mean square, the average signal level, or ASL, the signal strength, the absolute energy, the partial powers. I'm going to explain that tomorrow. The frequency centroid of the signal and the peak frequency. So all these parameters, I selected them in the settings of the software. But the system automatically extracts and calculates this information for you.
Yes.
Okay? And you can show also in tabular data. In this case, I selected just a couple of signals.
Okay.
But if I select more signals, I can do so. Let's say I want to select this. So you see I have 17 signals here.
Oh yeah.
And if you look at the tabular data, you have all the parameters from those signals. What channels detected the signals, and all the parameters individually for each one of the signals. Okay?
Okay.
Now, when you look at the waveform, you see that the scale on the y-axis is in millivolts.
Yes.
And this is in time.
Yes.
This is in milliseconds. All right? So, and these lines represent the threshold that we specify in the settings.
Okay.
So, if you look at how many times the signal crosses the threshold, that is the number of counts. if we magnify this part of the signal that crosses the threshold, how many times the signal crosses the threshold?
How many counts? 4.
Four times. Okay, this is the number of counts. So you see where the information comes from?
Yeah.
So, but all this information is not affected anymore by the preamplification or the gain used in the preamplifier.
Okay.
That's what I'm trying to tell you.
Okay, I see.
Mm-hmm.
So, let's say we get 80 decibel for pencil breaking, lead breaking.
Mm-hmm.
And then, I want to ask you again, what's next? What will be the next process? How we can estimate the sensitivity of sensors? Do we need to change the sensitivity of sensors or
No. You need to measure it only.
measure only?
The only thing that you can do to improve the sensitivity of the sensor, sometimes if the layer in between the sensor and the test piece is thick, that will affect the sensitivity of the sensor. You were telling me that you use a membrane. I don't know how thick is that membrane.
Let's say 1 millimeter thick.
1 millimeter thick.
Mm-hmm.
And is that the only thing that you put in between the sensor and the test piece?
No. That's one of the tests we had, but we recently we directly attach the sensors on the surface of granite.
And what is the difference in sensitivities when you use the membrane and when you use dry copper?
Actually, that's what I want to ask.
I mean, I would expect to be lower amplitude, the dry coupling, than with the membrane.
Excuse me?
The amplitude of the dry coupling, I would expect to be lower compared to the sensitivity with the membrane. I don't know if that is the case.
So if it has lower sensitivity, what kind of results we can expect?
Okay.
Okay, let me change my questions. What's the sensitivity?
Okay.
What's the sensitivity of sensors? Of course, it's the sensitivity of sensors, but
I don't want to confuse you. That is a more complicated term.
Actually,
I think you are familiar with, or you have seen, the calibration sheets.
Contained with the sensors?
Yes.
Yeah, we have many.
So you have the micro. I think it's these ones. You have the micro 30 or the nano 30?
Nano 30.
Nano 30?
Yeah.
So it's this one. And you should have something like this.
Yeah, this paper.
That's the calibration sheet.
Yeah, this is calibration sheet, right?
Yes. But that is obtained by comparing the sensor that you have there with a reference sensor face to face. Meaning that the reference sensor sends a pulse, and the sensor that you have there receives that signal, and this is the response of that sensor.
Okay.
And you see, I don't want to confuse you here because you have two scales. One is with reference to a 1 volt over a meter per second, and the other one is with reference to a 1 decibels per microvolt. And we don't use any of those when we are using the pencil brake.
What?
We are not using any of those. That's why I don't want to confuse you.
Okay.
What you can do, let me see if I have that information. No, I need to look for that information. But there is ASTM standard to check the sensitivity of the sensors.
Yeah, there's an ASTM standards for pencil lead brake test, right?
Yes, using an acrylic rod cylinder.
Anyway.
But let me prepare that information for you, and I will show it to you tomorrow.
Okay.
Because well, today is almost time to leave for me.
Okay.
It's almost 5 minutes left. But let me. What can I do right now? Yes. This is a paper. And, I have several standards that I can show you to check the sensitivity of the sensor. But let me look for it, and I will show you tomorrow.
Okay, I see.
No, they are not here. I need to look for them. Let me go. I think it's this one. Yes. This is for calibration of the sensors. This is the primary method that is used. It's a big block, and two sensors are mounted on each surface, separated by a distance. And the idea of having this block is to eliminate any reflection from the pulse generated by one of the sensors and the response received by the other one. So you see, this is the pulsar, and this is the receiver sensor. But that does not what I wanted to show you. This is another type, but that is a very practical. It is not here. I think it's this one. Yeah. It's this one. In 1976. There are several methods, but this is the one widely used. You see, you have an acrylic rod. This is, if I'm not mistaken, is 1.5 inch diameter. And you mount the sensor on this face of the acrylic rod, and you perform penciled breaks along this distance. You see? And then what you plot is the attenuation of the signal or the amplitude as you are moving away from the sensor.
Okay.
Usually what we do is mark several distances here.
Okay.
And at each distance we perform 3 penciled breaks, one here, one here, one here, one here, one here. And we calculate the averages. And then we plot the results on an amplitude versus distance plot. And that could be a way to compare the sensitivity of the sensor. For this one, you use the high vacuum silicon grease to mount this, and you can use that for comparison in your test specimen when you don't use any couplant, when you use just the dry coupling, and when you use the membrane.
Then?
Okay? So let's say that you perform penciled breaks 5 centimeters away from the sensor. And you measure the amplitude here.
Yep.
Please?
I'm sorry, but the connection is disconnected. Internet is disconnected, so.
Okay. So in this situation, you have the best conditions. You have a smooth surface where you have your sensor mounted. You have a good coupling with high vacuum silicon grease. And you perform the penciled break 5 centimeters away from the sensor.
Yes.
So you take note of the amplitude 3 times.
Okay.
all right? And you calculate the average. Then you do the same thing on your test specimen. Now with the sensor mounted on the test specimen, with dry coupling, okay?
Yes.
And perform 3 pencil breaks 5 centimeters away from the sensor.
Okay.
And then you compare those readings with the reading that you did on the acrylic. And you can tell how bad or how good is your dry coupling compared to this one.
Okay.
All right? And then you do the same when you use the membrane. Use the membrane to mount the sensor on your test specimen and perform 3 pencil breaks 5 centimeters away from the sensor and compare them again to this one and see if the readings are higher or lower. And that's how you can have a reference. If the sensitivity of the sensor is good or bad or both worse, depending on the couplant that you are using.
So what if the sensitivity is lower than the reference?
Well, you can make an estimation. You can have a relationship between the good coupling and the coupling that you have in your real application. Remember that you have the same reference. You have the pencil lead break.
Yes.
The pencil that you are using here is the same pencil that you are going to use in your specimen. You are using the same sensors. The only thing that you are changing is the couplant.
Yes.
So then you have there your comparison.
Yes, but
and you can tell if you are applying a specific force to the sensor for the dry coupling, with what force you get the highest amp. I don't know how you are holding the sensor to your test piece. With a strap.
You mean how to attach the sensor on the specimen?
Yes, how to hold it in place. Because you are not using a couplant.
Yeah, with wax. Using wax.
Okay, that is your couplant.
Yeah. That is kind of my couplant.
But then how you
It has cohesive.
How do you know the thickness of the wax in between the sensor and the test piece?
We don't know exactly.
Okay, and when you apply the wax, did you apply pressure to the sensor while the wax solidifies?
Yeah.
Okay. That's the thing that you can compare. Once you know that the wax is solid, then you can let go of the sensor. Then you can do one test when you know the wax is solid, and then maybe use a piece of tape around your test specimen holding the sensor. to see if the amplitude detected by the pencil lead ray is bigger or is the same.
Okay.
Okay?
Mm-hmm.
That can give you an idea if you can improve the sensitivity of the sensor by using the tape.
Okay, let me summarize what you explained. So we have, let's say we have reference amplitude,
Mm-hmm.
and when we want to carry out a new test, we have to conduct pencil lead breaking tests to compare with the value of from the reference specimen, right?
Yes.
And if, in case the amplitude of for new tests when we conduct pencil lead break test is lower than the reference, lower or higher, whatever. Anyway, when they have difference,
Mm-hmm.
and then do we have to change how to test the sensors, or anyway to increase the sensitivity of sensors for new tests?
No, let's say that you have your sensor here.
Sorry. I think you have to leave now, right? Maybe you can.
Ah, it's okay.
It's okay.
It's okay, don't worry. And you have the wax,
Yeah, right.
okay? Then you are going to perform the pencil lead break. Five centimeters away.
Yes.
Okay?
Uh-huh.
And you are going to measure the amplitude. Okay?
Mm-hmm.
What I am telling you, if you use a piece of tape around your sensor and the test piece
Mm-hmm.
to apply pressure to the sensor
Yes.
against the surface, and do another pencil lead break and measure that amplitude to see if with the tape around it the sensitivity is improved.
Yes.
If it doesn't improve, then the tape is useless.
Yes.
All right? And then you can compare this amplitude with the amplitude detected on the acrylic rod. When you have your sensor and you perform the pencil lead break again at 5 centimeters.
This is our reference point, right?
Yes,
This is our
that would
reference.
be, yes, because in this situation we are controlling everything.
Yeah, right.
Mm-hmm.
Okay. So.
But this is your real situation.
Yeah, that's right. So far I understand. So, in real tests, if sensitivity of sensors is lower than the reference, we should fix something, right?
Yes, try to decrease the thickness.
Yeah, that's
in
right.
this case of the wax that you are using. If you use the membrane, then you have to apply pressure to make the membrane thinner at the interface.
Okay, I understand.
That's the thing that is going to affect the sensitivity of the sensor.
Okay, I understand.
Okay?
Okay. Okay. I need time to arrange my idea.
No, that's fine.
Anybody?
That's fine.
I think I can understand now. So pencil.
I am going to prepare a small demonstration for tomorrow
Uh,
to explain you better what I'm trying to tell you. I have the acrylic cloth here. I can set up a small specimen to show you
okay.
what I'm telling you.
That will be helpful.
Yes, and to demonstrate you when you use dry copy and when you use different adhesives.
Okay. Thank you very
All
much.
right?
Mm.
We can do that tomorrow. That's not a problem.
Mm. Okay. Thank you.
Right? So I'll talk to you tomorrow at the same time, 6 p.m. my time, 8 a.m. your time.
Yes.
All right?
Same time for every day.
All right. So I'll see you tomorrow then.
Okay. Thank you for your explanation. See you tomorrow.
Have a good day.
Have a good night.
Yeah, good night.
Good night.